morning. Good morning. My name is Chandramouli. So, lecturer in mechanical engineering, working at Government Polytechnic, Warangal. So, my subject engineering materials. So, in that major topic, iron carbon equilibrium diagram. In this today's topic, various constituents of iron carbon equilibrium diagram. So first, before you analyze the iron carbon equilibrium diagram, uh, what type of constituents are occurs. So already you will see the how iron carbon alloying is iron carbon mixing is making, that means interstitial solid solution alloying means where is the vacancy positions is available. In that position foreign atom getting reacted or getting occupied. So in that type of alloying is called interstitial solid solution alloying. So before you construct or draw the iron carbon equilibrium diagram, first of all you will see the last class, you will see phase diagrams, what is the lower critical temperature, all these things. Before that you also see various constituents, various constituents of iron carbon system. So teaching aids are photos, diagrams, and animations. So recap, in this previous class we have discussed about phase and equilibrium diagram. Solid, so different types of alloyings is available. So in different types of alloyings, what is a solid? So three different types of alloying. So first one solid solution alloying, second one chemical compound, third one mechanical mixtures. So in that solid solution alloying, again subclassification is there: substitutional alloying and interstitial alloying, interstitial solid solution alloying. So next, cooling curves of pure metal, and next we will also discuss cooling curves of pure metal and alloys and solid solution alloying. So in our diploma syllabus we will see the binary system alloy. So two types of materials are mixing. That's why this is binary system alloying. Binary system equilibrium diagram only we will analyze. So next, the way solidification is represented on diagram. So you will see all these only last class. So today's objectives: on completion of this period, you would be able to understand various constituents that exist in the iron carbon equilibrium system. So the crystal structures and silent variants of those elements. So this is also very important topic for analysis of iron carbon equilibrium diagram. On completion of this period, you would be able to understand various constituents that exist in the iron carbon system, the crystal structure and other silent features of those elements. Okay, next. So already you see the allotropic form of iron. Already last class also discussed the allotropic form of iron. So you see this graph. So iron changes its structure. Iron changes its structure when heated or cooling. It is a reversible process. Iron changes its structure when heated. Iron has the ability to exist as BCC, means body centered cubic structure, or FCC structure, face centered cubic structure, depending upon the temperature. This ability is called allotropic form of iron. Already last class we discussed temperature versus time and which type of transformation occurs. Already this graph also you'll see that graph. So that's why this property very important property for the very important property for the iron is called allotropic form or polymorphism. So 1538 degrees centigrade is the melting point of the iron. So delta iron is the 1400 to 1538 degrees. You see the delta iron 1538 degrees centigrade to 1400 degrees. Delta iron exists. So it is a highly unstable form. So with the BCC structure. So next 1400 to 910 degrees centigrade. 1400 to 910 degrees centigrade, gamma iron exists. So it is the most stable form of iron. Most stable form of iron. So this exists the FCC structure, face centered cubic system. Next below the 910 degrees. Below the 910 degrees exists alpha iron with non-magnetic properties and alpha iron with magnetic properties. Alpha iron with magnetic properties called beta iron. So alpha iron with non-magnetic properties is called alpha iron. So it exhibits BCC structure. BCC structure, body centered cubic system. So in this diagram, so you will what is able to understand is, so in delta iron above 1390 degrees centigrade it returns to its BCC structure and it forms a ferrite. So in delta iron it forms a ferrite. It is a very softest material in the steel. So forms ferrite with carbon. Forms in delta iron forms with carbon. So between 910 and between 910 and 1390 degrees centigrade, iron has a FCC structure is known as iron as a form of austenite. With the carbon. Austenite. It is a stable form of iron, gamma iron. So in delta iron will form ferrite. And 910 degrees iron is crystallized BCC for which called alpha iron. So it is ferrite also forms ferrite with carbon. So this type of irons, you will see all these things. You will clearly construct the iron carbon equilibrium diagram. In the diagram clearly able to understand. So next slide will go for so in ferrite, so different types of constituents are occurs. In that first one is the ferrite. So ferrite so in a BCC crystalline form, ferrite is in the form of crystal BCC crystalline form, It is stable form of iron below the 912 degrees centigrade only up to 0.02 percentage of carbon exists in the solid solution. So it is the softest material in the iron carbon equilibrium diagram. So ferrite is the BCC structure and its stable form of iron below the 912 degrees centigrade it exists. It only carbon percentage is, so this is iron carbon intensal solid solution lying, so in that 0.02% only carbon. So in ferrite structure is, so body centered cubic structure. So in body centered cubic structure you will see the stick model illustrates the center atoms in the body centered cubic structure. So in body centered cubic structure, one central atom is there. You see the body centered cubic packing sequence. So remaining corners 1/8 part of the atom is there. So total number of effective number of atoms in body centered cubic structure is 1 plus 1 is equal to 1 plus 1 is equal to 2. 1 plus 1 is equal to 2. So that is the BCC structure for ferrite. So ferrite is the very softest material that exists below the 912 degrees centigrade in the iron carbon equilibrium diagram up to the 0.02%. So here these compositions, these constituents are very important. Which type of, how much amount of composition and which temperature it exists. So that is the very important factor. So both temperature and composition, both are very important. So next you will see the austenite. So these are the BCC structure, already analyzed all these BCC structures and the unit cell, all these things. Next you will see the austenite. So it is the most stable component of iron. It is the most stable component of gamma iron. So FCC structure, so it exhibits FCC structure. So FCC structure, high formability, high solubility of carbon, covers up to 2% of carbon can it dissolved in it. So it forms at 1148 degrees centigrade. Is the most heat treatment begins with this is single phase. This is the austenite, most stable form of austenite. In most stable form of austenite, you will see the structure is FCC structure, face centered cubic structure. This is a pattern for the atoms. This is the pattern of the atom center of the FCC of the each phase. So you will see in this FCC structure, the atoms are most tightly packed within in a BCC structure. This means that FCC structure is more dense. So it means more number of atoms is there. So there is no central atom. So there is only central atom at each phase. So 6 phases is there. In 6 phases, half of the atom is available in the each phase, remaining half of the atom is available in the space lattice. So that means 6 phases, half of them is 6 into 1/2 is equal to 3 number of atoms in the phases and corners. So each corner 1/8 part atom is there and remaining minus 1/8 means 7/8 part is available in the in the space lattice. So total number of effective atoms for face centered cubic system is 1 plus 3 is equal to 4 number of effective atoms in the face centered cubic system. So you will see the overall diagram. this half of atom that is only 6 phases. So finally we got 1 plus 3. So next one, delta iron. So delta iron presents extreme temperatures, that is 1492 degrees centigrade. So maximum carbon dissolved percentage is 0.08 percentage. 0.08 percentage. So one more component is that cementite. So stoichiometric intermetallic compound, hard and brittle, extract melting point is unknown. So already we will discuss iron carbon equilibrium diagram. So carbon content up to 2% is called steel. Okay, up to 2% is called steel. Greater than 2% 2 to 6.67 percentage is called 6.67 percentage is called cast iron. So after that 6.61 percentage in iron, 6.67 percentage in iron, carbon content does not dissolve, so that is a saturated point. So maximum amount of carbon dissolved in iron is 6.67 percentage. 6.67 percentage. So in that, so means of a set 6.67 percentage the constituents formed, that is called cementite. So Fe3C, this is the chemical form of the cementite is Fe3C. So it is the most hardest material. So that means stoichiometric intermetallic compound, hard, brittle, exact melting point is unknown. It is the hardest material form of iron carbon equilibrium diagram. This chemical form is Fe3C. Fe3C. So Curie point. So already you'll see. So gamma iron, delta iron, alpha iron. So and also you'll see the Curie point. So atomic level, non-magnetic to magnetic transmission. So up to 770 degrees below the all are magnetic properties. That magnetic properties changes at 770 degrees centigrade. That point is called Curie point. That point is called Curie point. So next, along with ferrite, austenite and cementite, intermediate components are formed. That the components are pierolite and ladderite. So you see the what is the pierolite? It is an intermediate mixture of ferrite and cementite. Intermediate mixture of ferrite and cementite. It has a distinct lamellar structure. It has a distinct lamellar structure. And consists of alternate layers of ferrite and cementite. So it is an eclectoid phase transformation of austenite at 723 degrees centigrade and having 0.3 percentage of carbon. So you see the iron carbon equilibrium diagram. This is easily understand. So first you will see which composition and which type of temperature it occurs. That is the very important. So it is an intermediate mixture of ferrite and cementite. So it has a distinct lamellar structure and consists of alternate layers of ferrite and cementite. So it is on eclectoid phase. So already these phases are getting invariant reactions are getting in invariant reactions are getting in iron carbon equilibrium diagram. So there are three type of invariant reactions is there. First one eutectoid, next eutectic, next periodic. Eutectoid, eutectic and periodic. So eutectoid means solid phase gives rise to solid, another type of two types of solids. So that type of reaction is called eutectoid reaction. Okay, so solid, one type of solid is gives rise to two types of solid. That means austenite is decomposed into two types of solids. That is the what is that is the uh, ferrite and cementite. So totally ferrite and cementite mixture is known as a perlite. Total to these two mixture is called ferrite and cementite. So this occurs at 723 degrees centigrade and the 0.83% of carbon. This is the eutectoid reaction. Very, very important. Eutectoid reaction. Solid one gives rise to two types of solids. Solids one gives rise to two types of solids. That type of reaction is called eutectoid reaction. Eutectoid reaction. So next one you will see the very, very important component is the ladaborite. So ladaborite is a mixture of austenite. And cementite. So it is obtained by eutectic phase transformation. Of liquid alloy. So it containing 4.3 percentage of carbon is cooled 1148 degrees centigrade. So below 723 degrees centigrade, ladaborite changes to perlite. So in this you will see the detailed ladaborite is the ladaborite means eutectic reaction. So eutectic reaction means liquid phase gives rise to two types of solids. Okay, here that means it is called eutectic reaction. Understand? Eutectic reaction means liquid gives rise to two types of solids. That means liquid form of iron is gives rise to austenite and cementite mixture. This type of this mixture of the combination is called ladaborite. So these mixture occurs at 4.3 percentage of carbon 4.3 percentage of carbon and 1148 degrees centigrade. So this is the very, very important for component. So below 723 degrees centigrade the ladaborite changes to perlite. So these are very, very important components: ferrite, perlite and ladaborite. So all invariant reactions, so eutectic reaction, eutectoid reaction and periodic reaction. So in periodic reaction, solid plus liquid is combination gives rise to another form of solid. So This type of reaction is called periodic reaction. So in iron carbon equilibrium diagram, you will concentrate how much composition on x-axis, so and which temperature it converts, which temperature these phases or transformation occurs, and what is the useful form of phase, which type of phase is conversion. All these are understand by using iron carbon equilibrium diagram. So in iron carbon equilibrium diagram, so suppose you will see this composition. So first one is the 100% of. So in iron carbon equilibrium diagram, most constituents are ferrite, first one alpha iron, gamma iron and delta iron. After that, main constituents are ferrite, pierrite, laterite and cementite. So after these constituents, ferrite, alpha iron, gamma iron, delta iron, ferrite, pierrite, laterite. Suppose you will see the animation how these constituents are occurs. After that we will explain. So first you will see the
Hello friends, welcome to Engineering Study Materials. In this video, we will discuss about the iron-carbon equilibrium diagram. Iron-carbon equilibrium diagram is the most important in mechanical engineering. So, let's we discuss about in this video. Iron-carbon diagram. Iron-carbon diagram is a graph which is used to know the material composition for the parts used in the industry. Iron carbon diagram. In the x-axis, it consists of a weight percentage carbon composition, and in y-axis it have temperature in degree Celsius. It contains lots of terms such as ferrite, austenite, pearlite, cementite, ladybirite, etc. So let's discuss in this video. So watch this video till the end to get more information. Phases in iron carbon diagram. Alpha ferrite solution of carbon in BCC Fe, that is iron. It is a stable form of iron at room temperature. The maximum solubility of carbon is 0.022 weight percentage. As we see in this diagram, alpha ferrite composition rate is as minute as 0.022 percentage carbon, and it transforms to FCC phase gamma austenite at 912 degree Celsius with the composition of 0.022 carbon, and when heating the
So in 2009, when I lived in San Francisco, I decided to see if I could hack the smart parking meters that the city was using.
alpha ferrite to 912 degree Celsius, it transforms into gamma austenite. Then the average properties of the alpha ferrite are 40,000 psi TS, it have the tensile strength, and 40% elongation in 2-inch, and Rockwell hardness between 0 or 90. And then comes to gamma austenite, solid solution of carbon in FCC iron. The maximum solubility of carbon is 2.14 weight percentage. When we add 2.14 percentage of carbon and heating to a temperature of 1395 degrees Celsius, we can transform the gamma austenite to BCC structure delta ferrite, as we see in this diagram. Gamma austenite transforms to delta at 1394 degrees Celsius with 2.14% of carbon. The average properties of the gamma austenite are 1,50,000 psi tensile strength, 10% elongation in 2-inch, and Rockwell hardness 440 and high toughness. It is not stable below the eutectoid temperature, that is 727 degrees Celsius, unless cooled rapidly. This is the eutectoid temperature line, 727 degrees Celsius. Then comes to delta ferrite solid solution of carbon in BCC ion. The same structure as a ferrite, stable only at high temperature above 1394 degrees Celsius and melts at 1538 degrees Celsius. Delta ferrite to then comes to Fe3C, that is the iron carbide or cementite. This is the intermetallic compound, is metastable. It remains as a compound indefinitely at room temperature but decomposes very slowly within several years into alpha iron and carbon in the form of graphite at 650 to 700 degrees Celsius, as we seen in this diagram. 650 to 700 degrees Celsius. It decomposes. Let's discuss the definition of these structures in the iron carbon diagram. Various phases that appears on the iron carbon equilibrium phase diagram are austenite, ferrite, pearlite, cementite, martensite and ladyburite. Austenite. Austenite is an interstitial solid solution of carbon dissolved in gamma ion in the FCC structure. Maximum solubility is 2% carbon at 1130 degrees Celsius. High formability. Most of heat treatments begin with the single phase.
యాండి నా ఫోన్ చూసారా?
It is normally not stable at room temperature, but under certain conditions it is possible to obtain austenite at room temperature. Properties. Tensile strength 1,50,000 psi as we seen above in the iron carbon diagram, and elongation 10% in 2-inch, hardness Rockwell hardness 40 approximately, and high toughness. This is the austenite structure, microscopic structure. Then ferrite. Ferrite is known as alpha solid solution. It is an interstitial solid solution of a small amount of carbon dissolved in alpha iron in BCC structure. Stable form of iron below 912 degrees Celsius. The maximum solubility is 0.025% of carbon at 723 degrees Celsius, and it dissolves only 0.008% carbon at room temperature. It is the softest structure that appears on the diagram because of the BCC structure. Properties. Tensile strength 40,000 psi, elongation 40% in 2-inch, Rockwell hardness above 90. Pearlite. Pearlite is a eutectoid mixture containing 0.80% carbon and is formed at 723 degrees Celsius on very slow cooling. It is very fine plate-like or lamellar mixture of ferrite and cementite. The white ferritic background of matrix contains thin plates of cementite. Tensile strength 1,20,000 psi, elongation 20% in 2 inch, at Rockwell hardness 20, Brinell hardness number 300. This is the structure which combines ferrite and cementite. Cementite or iron carbide is very hard, brittle, intermetallic compound of iron and carbon. As Fe3C contains 6.6% carbon, it is the hardest structure that appears on the diagram, exact melting point unknown. Its crystal structure is orthorhombic. It has low tensile strength, approximately 5000 psi only, but high compressive strength. Martensite, a supersaturated solid solution of carbon in ferrite. It is formed when steel is cooled so rapidly that the change from austenite to perlite is suppressed. The interstitial carbon atoms distort the BCC ferrite into a BC tetragonal structure BCT, responsible for the hardness of quenched steel. Ladyburite is the eutectic mixture of austenite and cementite. It contains 4.3% carbon and is formed at 1130 degrees Celsius. So this is a short video, friends, of the iron carbon diagram. So thank you for watching. If you like this video, please click the thumbs up button and share this video to your friends to gain knowledge, and don't forget to subscribe this channel for more videos. So thank you for watching. Temperature above 1394 degrees Celsius and melts at 1538 degrees Celsius. Appears on the iron carbon equilibrium phase diagram are austenite, ferrite, perlite, cementite, martensite, and ladyburite. Austenite. Austenite is an interstitial solid solution of carbon dissolved in gamma iron in the FCC structure. Maximum solubility is 2% carbon at 1130 degrees Celsius. High formability. Most of heat treatments begin with the single phase. It is normally not stable at room temperature, but under certain conditions it is possible to obtain austenite at room temperature. Properties. Tensile strength 1,50,000 psi as we seen above in the iron carbon diagram, and elongation 10% in 2 inch, hardness Rockwell hardness 40 approximately, and high toughness. This is the austenite structure, microscopic structure. Then ferrite. Ferrite is known as alpha solid solution. It is an interstitial solid solution of a small amount of carbon dissolved in alpha iron in BCC structure. Stable form of iron below 912 degrees Celsius. The maximum solubility is 0.025% of carbon at 723 degrees Celsius, and it dissolves only 0.008% carbon at room temperature. It is the softest structure that appears on the diagram because of the BCC structure. Properties. Tensile strength 40,000 psi, elongation 40% in 2 inch, Rockwell hardness above 90. Perlite. Perlite is a eutectoid mixture containing 0.80% carbon and is formed at 723 degrees Celsius on very slow cooling. It is very fine plate-like or lamellar mixture of ferrite and cementite. The white ferritic background of matrix contains thin plates of cementite. Tensile strength 1,20,000 psi, elongation 20% in 2 inch, at Rockwell hardness 20, Brinell hardness number 300. This is the structure which combines ferrite and cementite. Cementite or iron carbide is very hard, brittle, intermetallic compound of iron and carbon. As Fe3C contains 6.6% carbon, it is the hardest structure that appears on the diagram, exact melting point unknown. Its crystal structure is orthorhombic. Has low tensile strength, approximately 5000 psi only, but high compressive strength. Martensite, a supersaturated solid solution of carbon in ferrite. It is formed when steel is cooled so rapidly that the change from austenite to perlite is suppressed. The interstitial carbon atoms distort the BCC ferrite into a BC tetragonal structure BCT, responsible for the hardness of quenched steel. Ladyburite is the eutectic mixture of austenite and cementite. It contains 4.3% carbon and is formed at 1130 degrees Celsius. So this is a short video, friends, of the iron carbon diagram. So thank you for watching. If you like this video, please click the thumbs up button and share this.
So after you see the animation, so far microstructures of iron carbon system with different compositions, you will see the all these means. So alpha iron, delta iron, gamma iron. So alpha iron interstitial solid solution is a ferrite, 100% of iron. So very less amount of carbon is there. That's why structure is very clearly means the most softest material is the ferrite. Most softest material is the ferrite. So next one you see this is a microstructure of iron carbon system with different compositions. So you will see next one at exact 2.1 and I think exact 0.8 at exact 0.8 100% of perlite occurs. That is a it took that is a eutectoid reaction. That is a eutectoid reaction. So exact 0.8 100% of perlite is formed. So that is a eutectoid reaction. So the eutectoid means solid one gives rise to two types of solids. So solid one gives rise to two types of solids. So perlite is a lamellar type of structure. Lamellar type of structure is getting. So before 0.8, you will see the structure ferrite plus perlite, lamellar structure and white type of large grains are getting. That is the combination of perlite and ferrite. Perlite and ferrite. Exact 0.8 eutectoid reaction is getting. That is the eutectoid reaction. That is the eutectoid reaction at 100% of eutectoid reaction. So next after that we will go for the exact at exact 4.3%. Exact 4.3 percentage exact 4.3 percentage ledaborite is forming. Ledaborite 100% of ledaborite is getting. 100% of ledaborite is getting. So after that so iron carbide means Fe3C cementoid plus perlite, cementoid plus perlite. So these type of microstructures are getting, this type of microstructures are getting. So totally you will summarize today class. In this class we have discussed about ferrite and austenite and iron. Different types of irons: intentional, ferrite, austenite, perlite, ladderite. All these are intentional solid solutions of iron. Next we'll see ferrite, austenite irons are intentional solid solutions, and ferrite iron is having a BCC structure. Next, ferrite and different types of irons means gamma iron has FCC crystal structure, and delta iron is delta iron and alpha iron has a BCC structure, and perlite and ladderite are mechanical mixtures, cementite is a chemical compound. Cementite is a chemical compound, and iron carbon system exhibits all kind of alloy system. Okay, cementite is a chemical compound, perlite, ladderite is a mechanical mixtures, and remaining your ferrite, all these are the intentional solid solutions. That's why iron carbon system exhibits all kind of alloy systems, so we will see all these quiz also, all these questions. So this is the today's, we will final summarized which type of constituents are occurs. So that is the main thing. Thank you.